So we had shortcuts last time, right? How'd it go? Anybody want me to retract the shortcuts? Go back to the old way? Haha. Yes. Yeah. Yeah, let me just grab a new one from down here. Okay. 43. On 2.1. Okay, we got to get back there. No, it was on 2.2, not 2.1. 2.2, number 43. Eventually I'll get there. Okay, f of x equals 4x cubed minus 3x squared plus 2x plus 5 denominator x squared. Directions, find f prime of x. Yeah, what are we going to do with that denominator? Well, there is no, well, excuse me, there's a rule for doing quotients, but you haven't been told it yet. I think it's coming in like 2. Not today's, the 2.3, but in 2.4. So what are you going to do? Well, you could divide it term by term. You know, you could think of it as 4x cubed over x squared minus 3x squared over x squared plus 2x over x squared plus 5 over. So in other words, all we can do is try to do something algebraically. And couldn't we rewrite this then as 4x minus 3 plus what? 2, I'll say it this way, 2x to the minus 1 plus 5 times x to the minus 2. Now we should be able to apply the power rule, shouldn't we? If that's f of x, then what's f prime of x? Okay, using the power rule, this would be 4, this would be nothing. This next term would be what? Minus 2, x to the minus 2, minus 10, x to the minus 3. I'll stop. Let me pause there. Do you see what I did there? Now, I think what the book likes you to do is kind of translate this back into more normal polynomials. So then, usually, they like to see it like this. Which is really the same thing, just interpreting backwards what those negative exponents meant. So my guess is that's probably how they wrote the derivative. And that's all they were supposed to do for that problem. Yes. 59? Yep. '59 on 2.2. Okay. Okay, sales. Equation reads 8 points. Wow. This they got enough decimal points there, huh? 8.70947 t to the fourth minus 341.0927 t cubed plus, let's sneak one more in here, 48.85 0.752. T squared minus 30 point, no, 30,118.17 T plus 68,395.3. Okay, so there's the sales equation, and T stands for the year, huh? And a T of 7 means like 1997. Okay, so part A. Find the slopes of the graph for the years 1998. Okay, well, slopes of the graph means we want to look at the derivative. And by the way, I'm going to rewrite this. Instead of saying S, I'm going to change this to be S of T, because isn't that the variable T? And so what they're asking you to, what you need to do first is find this. Well, I don't know, it's a lot of horsing around. That would be 4 times this big old hairy thing, which is 32 point something or other T cubed minus 1,000, you know, I don't know, do you need me to do the derivative? Let me just make this comment. After you've got that done, then what they're asking you to do in part A is say, all right, now that I got that done, what's S prime at 8? Because they asked you for 1998. And according to their coding, 7 means 1997, 8 means. And then you got to do S prime at what? 11 and 13. So a lot of multiplication, but shouldn't be too bad. Now part B says, compare your results with those obtained in exercise, oh boy, I don't know. What's going on in exercise 12 of 2.1? Let's go see. Oh, okay, 12 on lesson 2.1 is exactly the same graph where you were supposed to eyeball the slopes. So they're just saying, now that we figured it out exactly, compare back with your estimates and see how your estimates came out. So that makes sense. And then part C says, what are the units for the slope of the graph? Okay, well, it's rise over run, right? And rise is what? Millions of dollars versus what, per year? So millions of dollars per year is what the slope is. And if the slope is positive, it means we're gaining that many millions of dollars each year. And if the slope is negative, it means we're losing that many millions of dollars per year. And there's a little bit of a losing streak there, isn't there? If you look at the graph, it's got a little bit of a negative dip, not much. Generally speaking, this is a very positive sales graph, but it does have a little bit of a dip. Is that enough information for you? Okay. Christina? 51? Okay. You might have that one. Let's just take a look. I do. Okay. Let me make sure. 51, what's it saying? It's saying take this, determine the points, if any, at which the graph has a horizontal tangent line. Okay. So after you find your derivative, what are they really asking you? If it has a horizontal tangent line, doesn't that mean that the slope of the tangent line would have to be 0? So my approach was, after finding the derivative, set the derivative equal to 0 and see what values of x it would take to actually make that come out to 0. Does that make sense? So I found my derivative, I took my derivative and set it equal to 0, and then I had to do algebra and try and solve for x. I could factor a little bit here. I took out a 2x, And that part, that's easy. That happens when x is 0. And then over here, this one's a little bit more of a pain. It's two answers, plus and minus the square root of 1.5. So I actually found 3 times when this graph should have a slope of 0. And that's what they asked you to find. When would the graph have horizontal tangent line? 3 times. Mm-hmm.
They also had a person finding 5/4 as an answer.
They did? They have a 5/4 for an answer too? Okay, let's...
0, -1.
Okay, let me think about this. So they have, how many answers do they have then? They have 4? Well, I've got 3 also, but they don't have the same 3 I do. Do they have...
No, they do. They have the y values also.
Oh, they plotted the y values too. Okay. So they've got 3 answers. See, I didn't do any y coordinates. How would I get the y coordinates for these points? I'd have to plug back into the original function. So to get the y coordinate, I got to come back here, and that would be what, -1? And this would be a little bit more of a mess, but you'd have to plug in minus the square root of 3/2. No. Anyway, that's... I didn't... They said it. Determine the points. Yeah, I guess they want to know the x and the y coordinate. Got it. Anyone else? Okay, well, a little bit of a, I guess you could say, kind of a moderate day. After kind of the earth-shaking stuff we did the other day, this is pretty mild. It's called rates of change. It's important. I didn't mean to imply it's not important. But what I'm trying to say is it's just kind of, I guess you could say it's like calculus light. Okay, it's just not, it's kind of a easy listening day. Okay? Maybe, I don't know. Now, a little bit of review to get us warmed up for this. What is that? A difference quotient. Let me write that down. Okay, let me ask again. What is that? What's another answer you could have given me? It's a slope. You bet. And one I'm going to guess you're probably not going to come up with. But when I tell it to you, it's got to do with rate, but I want to be a little more specific than that. This is actually an average rate of change. Average rate of change. Why is it average? Because the idea is this is a slope from 2 points. And when you have a graph, and you pick these 2 generic points, which is basically what's being done with that problem, and you kind of say, well, a straight line's pretty close. I'll take that as my slope, and that, as you can probably tell, is an average over that interval, right? I mean, obviously, what, right here, isn't the real slope less than this one? Isn't the slope of this tangent line right here slightly lower than the slope of that line? The slope is a little bit lower, and then over here, isn't it higher? But when you average it all out, yeah, so when you take 2 points and find the slope, that's an average rate of change. Okay, that's really important. Okay, now, next slide. What's this? derivative, right? That's what we were doing in lesson 2.1. Actually, we spent 2 days on that, so let's write that down. That's very important. Okay, now let me ask it again. What is this? So can you give me another answer for what, well, in other words, what's another way to say, what's a derivative? What are you finding when you find a derivative? Yeah, at any point. So instead of an average rate of change, this is they call it by 2 words. Either you could say it's an exact rate of change, or you could say it's an instantaneous. And I think the one in the book is mostly instantaneous. So that's not spelled right. There's no O in there, is there? Or I just went totally blank on the spelling here. That doesn't look right either. What is it? E-O-U-S, of course. Is that weird how sometimes you go blank? I've even had it happen occasionally. This is going to sound really dumb, and you're probably going to get me fired when I tell you, but haven't you ever written, I've even written the, and it didn't look right? Honest. Maybe it's because I have to read a lot of dissertations, and I'm reading all this stuff, and I'm like, haven't words ever looked strange to you? Even in well, some of them. Okay, a couple of you, thank you. But anyway, there we go. That's an N there. Okay. So the emphasis here is between that word and this word. So this is an average rate of change. And when you do the derivative, you have an instantaneous. Obviously, the instantaneous is better, but it depends on your use. If you were the company president and somebody said, hey, he said to you, hey, on the average, what was our growth rate over the last 12 months? Well, that's an average rate of change. You take the 2 points, one for the description at the beginning of the year, one for the description at the end, you connect them, and you do a slope. That's an average rate of change. So there are times for that. Well, you're going to notice there are questions that will ask you for average rates of change, and there are questions today that will ask you for the instantaneous rate of change. And you need to be able to differentiate between the two and know when to use which one. And a lot of emphasis on word problems today. And I've got to do a little business tutorial coming up here in a few minutes. Maybe I should do that right now. We'll come back. But here's my little business tutorial. I mean, you guys probably know a lot more about business than I do, but profit equals revenue minus costs. Everybody's familiar with that? That's what the P equals R minus C stands for. Now, some new stuff that we haven't talked about before. Usually in the book, they will talk about the cost function as C of X. So, like, the cost of their item is figured out thusly, and that's thought of as a function. But when you take the derivative of the cost function, C prime of X, that's called the marginal cost. That's a business term. In effect, it means, hey, what's the instantaneous rate of change of the cost? Because it's a derivative. But the term in business is marginal. So obviously marginal means rate of change. And then likewise, if R of X stands for the revenue equation, then R prime of X, the derivative of the revenue, is called the marginal revenue. So one thing that's pretty standard in business is they use the term marginal to stand for rate of change. Why am I doing this? Well, because they're going to be asking you in questions, find the marginal cost at when you sell 300 items. And so you're going to take the cost function, you're going to find the derivative, and then after you found C prime of x, you're going to find C prime at 300 or whatever the question says. Then I want to make sure and talk about this. I'm not quite sure why business uses the letters they do, but this is standard in business. Capital P is profit. They use a small p to represent demand. And this is a very important equation that relates demand back to revenue. Revenue equals X times P, and X is how many units you sell. So, if you take your demand times the number of units, you're going to get the revenue. By the way, what's another name for demand? Generally speaking, that's what you should charge. You know what I mean? If an item is really in high demand, well, let's face it, you can charge more for it, right? If an item is not wanted at all, well, if you're going to sell it, you better sell it for cheap, because otherwise nobody's going to buy it, right? The old supply and demand thing. If you've got, so anyway, R equals XP, where small p stands for demand. This comes up in problems today too. But here's the relationship between the words and the calculus. The word marginal is brought in whenever you're talking about rate of change, derivatives. So I probably went ahead, but okay. I'm not quite sure what that is. But I do want to talk about this. If you're in a science class, and especially physics, a lot of times you're interested in how high something is, like if you're studying moving objects. And usually the function will be the distance. If that's the case, then when you take the first derivative, you get the rate of change of the distance, which we call speed or velocity. And if you take the second derivative, you're going to get the acceleration. How quickly is your speed changing? And that would be, the snap back in the seat factor, if we're talking about a vehicle. Okay? Maybe even whiplash factor. Because that's a type of acceleration too. Hate to say it, but if somebody hits your car from behind pretty hard, that could quickly accelerate your car, and it often will cause neck injuries because, too quick of an acceleration. There is another term that's occasionally thrown out. What's the rate of change of the acceleration? It's sometimes called the jerk. How quickly did the acceleration change? That's sometimes called jerk. The term isn't real important, but my point is, do you see how I wanted you to see the relationship to distance. So if distance is our main equation, the first derivative is what's the rate of change of the distance? How quickly is my distance changing? That's called speed. And then how quickly is my speed changing? That's the acceleration. And how quickly is my so each time you take a derivative, you're kind of going to a new concept. And so you're going to see a few physics questions too. And this is how, at least I've given you a couple tie-ins with derivatives now. So this is example 4, I think, in the book. Let's just take a look at it. Given the position function of a diver who jumps from a board 12 feet, he jumps from a 12-foot high board, and he's in the beginning he's going 16 feet a second. So when he first comes off the board, his speed is 16 feet per second. So find the diver's velocity function. Okay, well, let me just put it to you this way. And I don't know, why did they say 12 feet high when the diagram says 32? Oh, I'm looking at the wrong one. Okay, he was 32 feet up. He was on a high board. All right. So let me just, this isn't real important, but let me tell you where I got the height equation from. Negative 16, that's gravity. And it's a negative because gravity pulls us downward. Okay, and it's negative 16 feet per second squared. Okay, then the 16t, that's his initial velocity. That's what the book said was his initial speed. And the plus 32 means he started that high up from the ground. Okay? So anyway, but that's not the important thing. If that's the equation, what's the equation of the velocity? Well, you got to go kind of to the bottom of the page. Easy derivative, right? Negative 16 times 2 is negative 32. And t to the first, reduce the power by 1. And the derivative of 16t is 16. And the derivative of 32 is goose egg. So what's the velocity of this guy? Negative 32t plus 16. At any time in seconds, we can calculate how fast he's going. Okay, how fast is he going at 0 seconds? So just go down there and do h prime at 0. 16. And isn't that what the problem says? Yeah, in the beginning he was going 16. How fast is he going after 1 second? Negative 16. What's the difference? Well, when you first go off the board, you are going up. And after 1 second, he's now going downward at a rate of 16. Okay, how about 2 seconds? Negative 48 feet per second. Obviously, he's speeding up, and you could find it at any part in the dot, right? When does he reach the top of his arc? Well, wouldn't that be when his height is wouldn't that be when the derivative is 0? Because what does that mean when a derivative is 0? The slope of the tangent line is horizontal, and wouldn't that say, so like here's his jump. He's on the board up here, and he goes, boing. And when he reaches the top, his height's going to level off, and then it's going to start going downward. And when will that equal 0? When will negative 32t plus 16 equal 0? Pretty easy to solve, isn't it? When t is a half. So at a half second, he's reached his height. Now, the question I've looked at up there is, when will he hit the water? Well, won't that be when his height is 0? Well, that's just an algebra problem. How do we find out when his height is 0? Set the function equal to 0. And I was able to factor out a 16. Actually, not just factor out a 16. Because it's an equation, can't I divide both sides by 16? So that's what I did in that third line. And then I could factor out divide both sides by negative 1. Hey, I can factor it. T plus 1, t minus 2. So there are 2 times when he is at the water level. 1 second before he jumped, and 2 seconds after he jumped. Well, the 1 second before he jumped is stupid, because he didn't start at water level. You know, what we're trying to show is this whole parabola. You got to remember what's goofy here. If the parabola was complete, here's what it looks like. But if the parabola was complete, it would look like this. So at minus 1 second, a second before he got to the board, he would have been jumping from the ground. Of course, you can't jump that high. And 2 seconds afterwards, he hits the water. So here's a case where, the minus, we're going to throw that out just because of practical matters. But that's where the other part of the parabola would be. Okay? So you're going to see problems with distance like that. Let's do one of these profit problems. This is number 41 in your book. So 41 says, a demand for a product is given by small p. Remember, I just told you a little while ago, small p stands for demand. Small p equals 50 over the square root of x. And they give you the domain anywhere between 1 and 8,000. That probably means that 8,000 is the maximum that factory can put out. So why would we possibly need to figure anything more? And why would we stop at 1? Well, you can't make a half of, whatever they're making. If they're making TVs, you sure can't try selling a half of a TV. You gotta have whole TVs for people to buy. Okay, so it makes sense that the domain is between 1 and 8,000. And then they give you the cost function. Okay, find the marginal profits for, and they give you these 5 different amounts, or 4 different amounts. Okay, what you notice they haven't given you? They haven't given you the revenue. But a little while ago I showed you how to find the revenue. Don't you have to take the demand times x to get the revenue? See it down here? So maybe my very first step is to take the demand function that they gave us and multiply it by x so that I can get the revenue. So that's what I'm doing right to the left of that. What is x times 50 over square root of x? Well, what I did is I rewrote this. What's another way to say this? Using fractional and negative exponents, how else could I say this? 50 times x to the negative 1/2 power. And then when you take 50x to the negative 1/2 times x, what do you get? What's x to the negative 1/2 times x to the 1? Keep the base and add the exponents. X to the 1/2, right? So that's where I got this from. I'm sorry, that's where I got the revenue. Here we go. 50x to the 1/2. Now, how do you find profit? Now you take the revenue and you subtract the costs. I'm sorry. Yeah, you take the revenue and subtract the cost from it. So, take this equation and subtract the cost function. Do you see why these are both minuses? I can't either. Sorry, making a backup right now. So, does everybody see why these are both minuses? Not now, okay? Yeah, I should have said skip, but I don't want to skip. So anyway, do you guys see why when you subtract an equation, don't you have to use the distributive property and everything has to be minus? Okay, so there's the profit. Now, what did the book say? Find the marginal profit. Whoa, what's marginal profit? That's the derivative of the profit. So now that I have the p of x function, I had to go ahead and find the first derivative, p prime of x. So now use your derivative rules. Okay, 1/2 times 50 is 25. What's 1 less than 1/2? Negative 1/2. And then this is derivative is just negative 0.5. Derivative here is gone. So there it is. There's my p prime of x. Now what's p prime at? Now you can answer the questions. What's p prime at 900? What's p prime at 1600? Etc. I did the 900 here. If you plug in 900, what is the square root of 900? Well, it's 30. And because it's a negative, It means, doesn't that mean 30 is in the denominator? And what's 25 over 30? It reduces down to 5/6. Negative 0.5 I wrote as negative 1/2. Do a little subtracting, you wind up with 1/3. So there's like answer A. What is the marginal profit when they're selling 900 items? Answer, 1/3. Which probably means, what's one, it's in terms of dollars, what's 1/3 of a dollar? 33 cents. So that means if you're selling 900 items, each one is giving you 33 cents profit. That's your marginal profit. And then, of course, it's going to be different. Next, let's just do one more. What's f prime at 1600? Well, what's the square root of 1600? 40. And what's 5 over 40? 1/8. And then you could do 1/8 minus 1/2. That's what? 1/8 minus 4/8, which is negative 3/8. Whoa, I mean, that means when you're selling 1600 items, you're actually going backwards a little bit. Why? I don't know. But that's where that dip in the graph was before. That's where you got the graphs doing one of these. So the slope is actually going downhill. Okay. So let me stop. I maybe went too fast on that. Anybody want to recap or go through any parts of that business thing? I probably did way too many new things at once there. Okay. Well, let's take some from other parts. How about looking at the very first section? What are they asking to do in number 2? Trade deficit. The graph shows the values, I, in billions, of dollars per year of goods imported to the United States. Everybody knows what a trade deficit is. That means we're bringing in more than we're sending out. And the really big import that changes a lot, that causes everything to be out of kilter here right now is oil. Bringing in all that Mideast oil, a lot of imports in dollars, and our exports, we've always had a ton of exports, but oil is causing, anyway, so we have deficits. All right. So the graph shows the value I in billions of bucks per year of goods imported to the United States, and E, number of goods exported from the United States. And at the for the most part, I take that back. Yeah, you notice how imports are higher than exports for most of the graph? That's our trade deficit. So what's the deficit? The vertical distance between the graphs. Okay. Approximate each indicated average rate of change. Okay? What's the average rate of change for imports between 1980 and 1990? So on your graph, what does that mean? Year 0 is 1980, so 1990 would be year 10. How could you find the average rate of change? This literally draws, you're making one point where, what is it, 0 comma, a hair over 200, where it begins, and then you're making another point at 10 comma, looks like 500, and then all you got to do is find the slope, average rate of change. And they said eyeball it, so, I said it was a little over 200. That's an estimate. Where is it? I don't know. I would say, what, 220, 230? It's not easy to nail it down exactly. So will all of us get exactly the same answer? No. Okay. Could you do the same thing for exports between 1980 and 1990? Yeah. Take the beginning point, take the ending point, find the slope. That would be the average rate of change. Okay, so that's average stuff. Fine. What if they ask you to find the exact rate of change in 1995? Well, you wouldn't be able to do it because did you notice I didn't give you an equation? And without an equation, you can't. So anyway, If they did, you could find the derivative and then find the derivative at 15. Okay, 3 through 8. Sketch the graph of the function and find its average rate of change over the interval. Well, let's take a peek at number 5. Yeah, let's see, do I have another blank here? Yep. Okay. So let's quickly plot the sketch of this graph. X squared minus 4x plus 2. So I'll tell you what, let's just get a couple points here. When x is 0, what do you get? 2. How about when x is 1? 1 minus 4 is negative 3. Negative 3 plus 2 is negative 1. How about when x is 0? We already did that. How about when x is 2? 4 minus 8 is negative 4 plus 2 is negative 2. How about a 3? Oh, by the way, let's save a little bit of time. What's the vertex? Do you remember how to do that? So I should do that up here. What's the vertex? Minus b over 2a? Remember that? So positive 4 over 2. So now we know this is the vertex. Well, if that's the vertex, then I must have another point here and another point here. And you can already see, at least in very rough format, okay, we got a curve that looks something like that. Now, it says from negative 2 to 2. Wow. We're going to be way up here somewhere. From negative 2 to 2, I'm making believe this parabola goes through there. I ran out of space. What would be the average rate of change? Well, wouldn't it be the slope of this thing? And so you can find the average rate of change. It's going to be pretty doggone negative, right? Okay. So they're just making sure you understand what average rate of change is. Let's do this more precisely. What is f of negative 2? If this is f of x, what's f of negative 2? 4 plus 4 is 8. It's 10, isn't it? And just to make sure we did it right, what's f of positive 2? Did I copy that wrong? What did I do? Copy the problem wrong? It's plus 2. How did I get down here? What did I do? Let's see. 2 squared is 4. 4 minus 8 is no, that's negative 2. That's correct. Right? Okay. So what are my 2 points? Negative 2, 10, and 2 comma negative 2. What's the slope? y2, I'll use this as 0.2, y2 minus y1 over x2 minus x1. So what's the average rate of change over the interval from negative 2 to positive 2, negative 3. Just a slope. Okay, let's go on to the next part. 9, 9 and 10. Use a graphing. Okay. I don't know. Should we do another marginal cost problem, number 18? Well, that's pretty easy. If they gave you the cost, how do you find the marginal cost? Take the derivative of the cost function. So what is? Let's just quickly do that one. New page. Number 18. Cost is equal to 104,000 plus 7,200x. Therefore, the marginal cost must be C prime of x, and that's got to be equal to, well, that's a really easy derivative, isn't it? Just 7,200. So what's that telling me? In that crazy cost function, the rate of change is always the same. It's always $7,200 per unit. So in other words, that's pretty simple. That's every time you sell another one, your marginal cost is going to be the same. What's the final question here? Find the marginal cost for producing X units. There it is, 7,200. And we could probably just put a $sign on there and we got it. All right, running out of time. Assignment. I didn't look it up, so we'll quickly do it now. One to 41 odds. See you tomorrow. Tomorrow at the later time.